Ayubowan, today we are going to learn Unit 13 Electrochemistry. First, let's see what is electrochemistry. Electrochemistry is the study of the exchange between electrical energy and chemical energy related to chemical reactions. So, here the chemical energy dealing with chemical reactions that produce electricity, which the energy released by a spontaneous reaction is converted to electricity, and or electrical energy is used to cause non-spontaneous reaction to occur. In these specific systems, the reactions involve electron transfer, and they mainly a pair of reactions, oxidation and reduction or redox. You have learnt redox reactions, so they are familiar to you. In redox reaction, electrons can flow from oxidized species to reduced species. Let's consider some concepts related to this lesson. One of them is conductivity. Consider this subject. Here you can see the current is flowing through the object. The resistances are capital R. The length of the object is simple L, and the area of the cross section is A, capital A. Here electrical conductance, the symbol is capital G. It is equal to 1 over R. Here you know this capital R is electrical resistance. The relationship between conductance and the resistance is given by this equation. Conductance equals 1 over R. So, 1 over R equals A over rho L. This rho is the proportionality constant, and it is called resistivity. 1 over rho is called conductivity, that is inverse of resistivity. 1 over rho equals K, that is conductivity. So, that is also called specific conductance, that is represented by the symbol K, that is Greek kappa. The SI units of conductivity are Siemens per meter, but quite often conductivity is expressed in Siemens per centimeter. Conductivity of a material in Siemens per meter is its conductance when it is 1 meter long and its area of cross section is 1 square meter. Here you can see the relationship between resistivity and conductivity. Resistivity is usually used for electronic conductors, and conductivity is usually used in electrolyte systems. Metals are electronic conductors. They conduct electricity by electrons. Liquids and solutions of some compounds can conduct electricity by ions. They are called ionic conductors. Depending on the nature of the compounds, they can be classified as follows. So, these electrolytes can be classified into 3 groups: strong electrolytes, non-electrolytes and weak electrolytes. So, here you can see some examples for strong electrolytes. Sodium hydroxide, HCl are strong acids. In addition to them, aqueous solutions of ionic compounds are also strong electrolytes, like sodium chloride, potassium chloride. Next, weak electrolytes, they are weak acids and weak bases. For example, acetic acid, ammonia. Water is also a weak electrolyte. So, both the strong electrolytes and weak electrolytes conduct electricity. They can conduct electricity because they are having mobile ions. Non-electrolytes, they do not conduct electricity. For example, you can give benzene, glucose, kerosene. They are non-electrolytes. They do not have mobile charge carriers. Therefore, they do not conduct electricity. Now let us see what are the factors affecting conductivity. There are 4 factors. First one, nature of the ion or the solvent. Next, nature of the solvent. Concentration of the solute. Last one, temperature. When we consider the nature of the species or the solvent, it determines the presence of mobile ions. Aqueous solutions of strong electrolytes can conduct electricity due to the presence of mobile ions. In molten state, ions gain mobility, therefore they conduct electricity. Weak acids and weak bases can conduct electricity as they react with water to produce ionic species through partial dissociation. In solid state, ionic compounds cannot conduct electricity because they do not have mobile ions. Now here you can see conductivities of various water samples and solutions at 298 Kelvin. Conductivity of distilled water is around 1 to 20 microsiemens per centimeter. 0.1 mole per cubic decimeter potassium chloride solution has conductivity of 1480 microsiemens per centimeter. 0.1 mole per cubic decimeter KCl solution 12,400 microsiemens per centimeter. Now here you can see the effect of concentration of the solution. Now conductivity of dilute aqueous solutions decreases with the decrease in concentration, that is due to the decreased amount of ions and interaction of ions upon dilution. So from this table you can see that with increasing concentration, conductivity has increased for the same KCl solution. And when we consider sea water, it has lot of ions, therefore it has higher conductivity. It is about 40,000 microsiemens per centimeter. When we consider the temperature, when temperature increases, conductivity increases approximately about 2% per each degree of centigrade. Effect of temperature on conductivity. So here you can see, here the concentration is constant, say 1 mole per cubic decimeter KCl solution. So with increasing temperature, you can see conductivity increases. At 0 degrees Celsius, it is 6.5 into 10 to the power 4 microsiemens per centimeter. At 13 degrees Celsius, 9.8 into 10 to the power 4 microsiemens per centimeter. At 25 degrees Celsius, it is 1.1 into 10 to the power 5 microsiemens per centimeter. So there you can see, with the increase of temperature, conductivity has increased. For 0.1 mole per cubic decimeter, the same situation. For 0.01 mole per cubic decimeter, you can see the same situation. When we increase the temperature, conductivity increases. Here you can see the speeds of ions in an aqueous solution under the potential gradient 1 volt per centimeter at 298 Kelvin. So current carried out by an ion at a given temperature and an electric field depends on the concentration of ions and their speed. The speed of an ion depends on its charge, size and potential gradient of the applied electric field. According to this table, H plus and OH minus ions have the highest speeds due to relatively small size. Thus, these ions are major contributors for the conductance of an aqueous solution. Conductivity of a solution plays an important role when analyzing the ionic content of a water sample. In practice, conductivity meters are used to measure the conductivity of a solution. Such measurements can be used in evaluating salinity, calculating solubility products. Now let us consider electrodes in equilibrium. First, metal ion electrode. So this is single electrode cell. Here the metal is dipped in a solution of its metal ions. A system where a metal is in dynamic equilibrium with its ions can be defined as an electrode. Magnesium solid is converted into Mg2 plus ions and 2 electrons. So here magnesium solid is converted to Mg2 plus ions, while in the other direction Mg2 plus ions in the solution are converted to magnesium metal. So both reactions can occur. A charge separation occurs at the interface between metal and the solution or water. The tendency of this charge separation depends on the activity of metal. Systems are in dynamic equilibrium. Two reactions can be written as given below. So here you can see in the first reaction, it's reversible reaction, magnesium 2 plus gains 2 electrons to convert into magnesium solid. Likewise, copper 2 plus gain 2 electrons to convert into copper solid. So these equilibria are usually written as reduction reactions. You know, reduction reactions, they are the magnesium 2 plus has reduced to magnesium solid. So the oxidation number has decreased here 2 to 0. Now here the metal rod is dipped in M plus solution. Due to the quick build-up of electrons on metal rod, it is surrounded by a layer of positive M plus ions. M plus ions are attracted to this negative charge on the metal. Some of them reclaim their electrons and stick back on the metal rod. Here the charge separation occurs at the interface between metal and the solution. A dynamic equilibrium will be established when the rate at which ions are leaving the surface is exactly equal to the rate at which they are joining it again. There will be a constant negative charge on the metal rod and a constant number of M plus ions around the rod. Once this situation is achieved, such a system is defined as an electrode. A system where a metal is in dynamic equilibrium with its ions is known as electrode. Here you can see the metal ions, M plus ions, are in equilibrium with metal solid. All these equilibria are usually written with the electron on the left hand side of the equation, that is as a reduction reaction. So you can see the reaction has written as a reduction reaction. Ability to reach equilibrium can be expressed as electrode potential. Potential difference is usually recorded as voltage. The unit is volts. Absolute voltage between the metal and the solution cannot be measured, and it is usually compared with a standard system called reference electrodes. This is copper electrode. You can see it is dipped in a copper sulfate solution. So there is an equilibrium between copper solid and Cu2 plus ions. There are 3 reference electrodes. Standard hydrogen electrode, it is theoretically important. Second, standard Calomel electrode, and standard silver chloride electrode. So both of them are practically important. Standard hydrogen electrode. So the conditions used in standard hydrogen electrode are 100 kilopascal or 1 atm pressure of hydrogen gas, the temperature of 298 Kelvin, and 1 mole per cubic decimeter concentration of the H plus ions in the solution. Here you can see as hydrogen gas flows over the porous platinum, an equilibrium is established between H2 gaseous molecules and H plus ions in solution, which is catalyzed by platinum. Here the reaction is given, the equilibrium between H plus ions and gaseous H2 molecules. Now let us see how to measure the potential of an electrode. The standard hydrogen electrode is attached to the electrode system, for example, a piece of magnesium or zinc in a solution containing magnesium or zinc ions as considered earlier. A conducting platinum wire is introduced to connect the voltmeter and a salt bridge. So, here you can see how to measure the standard electrode potential of zinc 2 plus system. So, there you can see the hydrogen standard hydrogen electrode has connected to this zinc 2 plus system. Salt bridge is used to complete the electrical circuit, making a liquid junction. Salt bridge is a glass tube filled with a solution of an electrolyte like potassium nitrate. The ends are stoppered by cotton wool or agar gel to prevent mixing of the contents of 2 beakers. Each electrode is defined as a half cell. There you can see the reactions related to each half cell. Zinc is converted into zinc 2 plus, where H plus is converted into H2 glass. So, electron flow occurs from the zinc electrode to the hydrogen electrode. Here the ability of zinc to form zinc 2 plus ions is higher than the ability of hydrogen to form H plus ions. Therefore, the position of magnesium 2 plus equilibrium will be more to the left than that of H2 H plus equilibrium. There is a greater buildup of electrons between charges on the 2 electrodes, and the potential difference can be measured with a voltmeter. This is actually the standard electrode potential of zinc 2 plus zinc system. The measurement of electrode potentials allows us to determine the position of the metal ion equilibrium with respect to the equilibrium involving hydrogen. The standard cell potential E0 of the hydrogen electrode is taken as 0 volt at room temperature. The potential produced is measured as voltage. Zinc has greater amount of negativeness. Standard electrode potential of zinc 2 plus zinc electrode is minus 0.76 volt. Maximum possible voltage at any situation is known as electromotive force, EMF. Then let us see how to write electrode notations. Here it is given the hydrogen electrode notation for hydrogen electrode. Here also you can see the how to measure the electrode potential using standard hydrogen electrode. So, the half cell with metal M electrode under standard conditions is attached to standard hydrogen electrode. Here some typical standard electrode potentials are given for Mg2 plus aqueous magnesium solid combination. Standard electrode potential is minus 2.37. Zinc 2 plus zinc, it is minus 0.76. Cu2 plus copper, it is a positive value, plus 0.34. Ag plus silver solid, that is 0.8. Then let us consider metal insoluble salt electrodes. If a metal is in contact with the solid salt of the same metal, such electrodes are known as metal insoluble salt electrodes. Examples: Calomel electrode, silver chloride electrode. In Calomel electrode, platinum wire is used to establish the electrical connection with an external circuit. A standard solution of KCl or potassium chloride is used for the electrical conductance. This is silver chloride electrode. This electrode has a silver wire coated with silver chloride, which is in contact with potassium chloride electrolyte. Important part of this electrode is the tip that connects electrode with the external solution. Here you can compare these two electrodes, metal insoluble salt electrodes, silver chloride reference electrode and Calomel electrode. Then let us see what are the gas electrodes. First one, standard hydrogen electrode, the most fundamental reference electrode in electrochemistry. By definition, its equilibrium potential is considered 0 at any temperature, because this electrode was chosen as an arbitrary 0 point for electrode potentials. A 0 point is needed since the potential of a single electrode cannot be measured. Only the difference of two electrode potentials is measurable. All electrode potentials are expressed on this hydrogen scale. It is a hydrogen electrode with an electrolyte containing unit concentration of H+ ions and saturated with H2 gas at unit atmosphere pressure. This electrode can be somewhat inconvenient to use because of the need to supply hydrogen gas. Therefore, other reference electrodes, for example, Calomel or silver chloride electrodes, are often used instead, but the measured electrode potentials can be converted to the hydrogen scale, also called normal hydrogen electrode. Here is a diagram of hydrogen electrode. Next type of electrodes, redox electrode. Both oxidized and reduced species must be present in the solution when defining a particular redox electrode. A platinum wire can be used to establish the electrical connection with the external circuit. Here you can see Fe2+, Fe3+ redox electrode system. In this diagram, you can see how to measure the electrode potential of redox electrode using standard hydrogen electrode. So, it is attached to standard hydrogen electrode. So, here feasible cell reaction is also given. Fe3+ plus H2 gas is converted into Fe2 plus H+. So, here the balanced equation has given when the cell is in process. Next, electrochemical series. When writing an electrode reaction, a single arrow is used because there is a current passing through and it is not in equilibrium. When electrode is isolated, it can exist in equilibrium. Electrode potentials of half cells are given as redox potentials. Electrochemical series can be built up by arranging various redox equilibria in order of their standard reduction potentials. Now, here you can see most positive E0 values are placed at the top of the electrochemical series. Usually, the most negative E0 values are placed at the top of the electrochemical series. Here you can see the most positive values are on the top and the values are arranged in the decreasing order. Okay. Here it is given a simple way to remember the reactivity series: potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, copper, silver, gold. So, most reactive metals are on the top and least reactive metals are at the bottom. Next, let us see what are reducing agents and oxidizing agents. A reducing agent reduces some other chemical species. That means that a reducing agent gives electrons to another chemical species. Conversely, an oxidizing agent oxidizes something else by accepting electrons. According to the above electrochemical series, magnesium is good at giving away electrons to form its ions. Hence, magnesium is good reducing agent. On the other hand, copper does not form its ions very readily, and its ions easily pick up electrons to convert to metallic copper. Hence, copper 2 ions must be good as an oxidizing agent. Metal ions at the bottom of the series are good at picking up electrons. These are good oxidizing agents. The oxidizing ability of the metal ions increases down the series. The more negative the E0 value, the position of the equilibrium to the left and the tendency of the metal to lose electrons. Therefore, the more negative the value, a particular species is stronger reducing agent. The situation is opposite for the species at the bottom of the electrochemical series, as these are good oxidizing agents. When two metals are in contact, metals with higher negative standard potential prefer to be in ionic state, while can be used to reduce ions of the other metal in contact. Next, electrochemical cells. Let us see how to construct an electrochemical cell. So far, we have considered combinations of a hydrogen electrode with the different electrodes as we measure standard reduction potential. It is interesting to consider that happens if a zinc half cell is combined with a copper half cell through a voltmeter and the solutions are connected via a salt bridge. Now, here copper electrode is in contact with zinc electrode. The solutions are connected through a salt bridge which is containing potassium nitrate. The potential generated due to presence of two different electrolytes in electrode components is called liquid junction potential. This potential can be minimized by using a salt bridge to join the two electrolytes. Salt bridge is a medium consisting of an electrolyte such as potassium nitrate or potassium chloride. The two ends of liquid junction are dipped in respective electrode units. This liquid junction can also be made by a permeable membrane or porous partitioning which allows ions to pass through it. Here you can compare these two electrochemical cells. See the difference between them. In the first one, there is a porous disc in between the reducing agent and the oxidizing agent. But in the second, electrolytes are separated and they are connected via a salt bridge. In the first one, the porous disc allows ions to pass through it. Here's the two equilibria which are set up in the above half cells. You can see the cell reaction. Cu2 plus zinc convert into Cu solid, copper solid, and zinc 2 plus. So, the reaction continues to take place till the opposing voltage reaches the value 1.1 volt, at which the reaction stops altogether and no current flows through the cell. Any further increase in the external potential again starts the reaction, but in the opposite direction. There are two types of electrochemical cells: galvanic cell and electrolytic cell. Here you can see the comparison between those two cells. In galvanic cell, energy released by spontaneous redox reaction and it is converted to electrical energy. But in electrolytic cell, electrical energy is used to drive non-spontaneous redox reaction. If the cell is able to produce electricity through a spontaneous reaction, then it is called a galvanic cell or a voltaic cell. If the reaction is not spontaneous, then an external source of current is required to operate the cell. Such a cell is called an electrolytic cell. In a galvanic cell, oxidation and reduction reactions are responsible for the operation of the cell. When the cell is in operation, electrons released at one electrode due to oxidation travels to the other electrode, resulting in reduction. The electrode at which oxidation takes place is called the anode, and the electrode at which reduction takes place is called the cathode. The overall cell reaction is obtained as combination of reduction and oxidation half reactions. Therefore, for the galvanic cell consisting of zinc and copper electrodes, which is named as Daniell cell, the overall reaction is given by the sum of the two half reactions. So, here the cathode reaction is given. It is a reduction half reaction. So, cathode is at the right hand side. The reaction Cu2 plus gain electrons to convert into copper solid. So, there you can see the Cu2 plus is reduced to copper solid. Anode reaction, zinc solid converts into zinc 2 plus. Anode is at left hand side. There you can see zinc has oxidized to zinc 2 plus. Anode reaction, zinc solid converts into zinc 2 plus. Anode is at left hand side, and you can see the zinc has oxidized to zinc 2 plus. That is oxidation half reaction. So, that is all for today. Next, we can start from cell notation. Thank you.